All right, hey guys, so we are going to go over these notes for today, but I really want you to take the time to try it yourself. So pause the video here. You're going to work through questions 1 through 6. Take some time, see if you can do it, because I'm just going to be posting these solutions on here. So make sure that you've worked through it, you know where they're all coming from. All right, so again, pause the video now and then continue on once you've completed 1 through 6. Okay, hopefully you paused and you tried it yourself, because that is the best way for us to learn. And now we're going to go over it together. So in this problem, all right, guys, so at this point my audio cut out, so I'm just going to caption this video right now. So I went over to Staplet.com, looking at the scatter plot here. I'd put in my data. Hopefully you did the same. Going down to calculate that least squares regression line. And I zoom in here. You can kind of see where the point for 5 should go, right? If you're looking at 5 on the X, you look up to the line, you should be able to see, and then it does give us our equation for the line as well. So I copied and pasted it over here. Some important things I want to point out to you here. The first one is going to be on top of that y. Notice on top of the y is that it's a caret, basically, right? That is really important. So if you did not copy that over, make sure that you do add that in to your notes now. That y with that symbol on top is what we call y hat. So y hat, what it means essentially is that it is a predicted value. And so we're going to add that into our notes here. We're going to make a note that y hat means predicted y. So essentially here, right, it's just talking about how this line is predictions. It's not a guarantee. We don't know for sure what's going to happen, but these are our predicted y values based on the data that we collected. Now with this equation, sometimes it's helpful to rewrite it in terms of context of your problem. So in this problem, understanding that y and x, right, y was our distance traveled, x was the number of rubber bands. Again, that follows for explanatory versus response variable. So explanatory was x, response was y. And therefore our rubber bands was x and distance traveled y. So to rewrite the equation with that context, you can write distance predicted, so we write distance with the hat, equals 25.3333 plus 7.4638 parentheses rubber bands. And so why this is really helpful, it's going to help you with predicting later on. It's going to help you relate back to context. So when you have to interpret, it's really good that you remember what x and y represent. So when we interpret the y-intercept, when we interpret slope, this is really helpful for that as well. All right. So then looking at question 2, use the regression line to predict the distance Barbie travels for 5 rubber bands. Here again, we're saying that 5 is our x. And if you look above, right, where we just wrote it with context, that makes it really easy to recognize where I'm going to plug 5 into. I'm plugging 5 in for rubber bands because it's 5 rubber bands. And so we get y, and really I should add in a y hat there. I believe I will in a few seconds. Y hat equals 25.3333 plus 7.4638 times 5. I got 62.6523 centimeters. And then I can rewrite that with the distance predicted equals that value. And again, remember, this class is all about communication. So I want to communicate clearly that this is a predicted distance. So it's really important that you have that symbol, and when we talk about it later, that you continue to remember to mention predicted. All right, question three, one of the group's members later found the measurement for 5 rubber bands was 64 centimeters. Was my prediction too high, too low? How far off? So for how far off, I'm just going to subtract. I'm going to take the value that was real and subtract away the value that we had found when we predicted. I got 1.347 centimeters. And so I said it was 1.347 centimeters too low. So what we're learning right here in question 3, this is actually like a big idea for today's lesson. When I find the difference between the actual value and the predicted value, that is what we call a residual. So residuals, again, what we do is we take the actual value and we subtract away the predicted value. So 64 minus our predicted 62.6523. So on the side of your notes here, you want to write residual equals actual minus predicted. And as I'm writing this, I will also underline, so actual minus predicted, it's really important you remember it's A minus P. And so one thing you can remember is AP, it goes in the order AP, like AP Statistics, the class we're taking. All right, and then in my sentence, I said it was 1.347 centimeters too low, but we really in this class want to avoid using the word it because that is not very clear. We're not communicating very well. What is it, right? And so I'm going to cross out that it here and I'm going to reword it in context of the problem that we're dealing with. So with this problem, it's not it is the predicted distance because our predicted distance was too low from the actual. So I said the predicted value was 1.347 centimeters too low. In question 4, it says predict the distance that Barbie would travel if the group used 20 rubber bands. Would you trust this prediction more or less than the prediction you made in number 2? So again, here I plugged in 20 for X. I found Y to be 174. Oh, and we're going back to the scatter plot. So here I'm just pointing out, in the scatter plot, when we had to find 5 in question 2, 5 was right there on the line, right? It was right between the point at 4 rubber bands. And the point for 6 rubber bands. It was in the middle of them. And just the fact that there was one above and one below, that helps me kind of estimate, okay, I think 5's probably in the middle of these two. I mean, we see the pattern for below and above continuing. But if I want to predict 20, well, 20 is way off there, off of this scatter plot and off this line. So I don't feel as confident that by time I get to 20, it's going to follow the same pattern. It's possible that there could be a plateau or that there could be a large spike. And so I don't know for sure what's going to happen at 20. And I just, feel less confident than I felt with just 5. And so going back to the notes here, again, I wrote down that I felt less confident because we were further out from the current data that we had collected. Now, again, this is another big idea for today. If we use the linear regression to predict a number that is outside of our current data, so currently we are from 0 to 7 rubber bands, that is what we call extrapolation. So that's extrapolation. When I plug in an x, that goes outside of the range of my current x values. So right now our x's were from 0 to 7. Because 20 is larger than 7, that's extrapolation. Okay, moving on then to question 5. What is the y-intercept? Oh, one more thing to mention. Extrapolation is something you never want to do. I say never lightly. It's not a good thing, okay? We don't want to extrapolate data. I just scrolled back up to show you between 0 and 7, so I'll take a second. Sorry about this, guys. I made the video like 5 times, so we are making it work right now. So again, scrolling back down, question 5 is going to ask us, what is the y-intercept of the equation of the regression line? What does it mean? So what you might notice is that these equations are written a little bit differently than normal. It actually was y hat equals, and we call it a and b, not m and b. So y hat equals a plus bx, where first was the y-intercept, then the slope and x. And remember, the y-intercept is when x is 0. So it's the ordered pair 0, comma, whatever the y-intercept value is. And so we found our y-intercept, and now when we interpret it in the context of the problem, remember we're interpreting for when whatever x is, and when we wrote it, we said x is rubber bands. So when x is 0, y, or the distance traveled, is our value. And so here, this is what I wrote. When there are 0 rubber bands, x, the distance traveled is 25.3333 centimeters. Now, let's take a second and think about this. My interpretation says that at 0, the distance is 25.3333. But back up in the table, at 0, we got 25. We didn't get 0.3333. So remember, this is talking about the equation, which is the predicted values. So it's really, really, really important that in here you add in the predicted distance traveled. Moving on to question 6, what is the slope of the equation? So the slope is 7.4638. Now with slope, and I kind of wrote it there a little bit, but remember, slope is rise over run, or the change in y's over the change in x's. So we think about it kind of like a fraction. And notice here, I don't actually have a fraction. I have a value, but I could always put any number I want over 1 to kind of turn it into a fraction. And so what ends up happening when I put that slope over 1, I see that the y's change by 7.4638 every time the x changes by 1. And so typically, really all the time, this is how it's going to work, is that we're going to affect x by 1. We're going to increase x by 1. And then we're going to see what does the y value do. All right, this is that idea of independent and dependent. So here, what I wrote was when we add 1 rubber band, so there we go, when we add 1x, the distance traveled increases by 7.4638 centimeters. That distance traveled being our y value. So we talked about x moves 1, y moves 7.4638. Now remember, really important again, this is only the predicted distance traveled, right? Not every time that I add 1 rubber band does it perfectly go up by 7.4638. So it's important here that we write in predicted. All right, so we're going to move on to the important ideas for today, these learning targets. We've got 3 of them. Learning target number 1. This is predictions, all about predictions. So we're going to start by writing the equation y hat equals, remember I said it's a little different, a plus bx. So y hat is predicted y, a is your y-intercept, and b is your slope. So let's take a second and label those. Predicted, y-intercept, and slope. All right, now important note here, be careful of extrapolation. Remember, we do not want to extrapolate. So when we extrapolate, it means that we are trying to estimate outside of our current range of values for x. And so that's going to be an extrapolation. Learning target number 2. This one is about residuals. So for residuals, our equation is the residual equals actual minus predicted. So AP, remember AP stats. Another way that you could write it is just very simple abbreviation, R equals A minus P, or RAP. So you could also remember this by thinking RAP. And then let's come up with a fill-in-the-blank sentence to interpret these residuals. So we're going to write this fill-in-the-blank. The actual context, so the actual, let's say, distance traveled was 1.3 centimeters above or below. Depends on what you are. So if your residual is positive, negative, kind of like with z-scores, above or below. The predicted value for, and then here's another fill in the blank, x equals number. So before on the first page when I said the actual distance was 1.347 grams below the predicted value for x equals, and I don't say x equals, I say for 5 rubber bands. So for that x equals number, again, I'm just taking the number that I plugged in, 5, putting it back into context. So 5 rubber bands. All right, and learning target number 3 is about y-intercept and slope. So here we're going to come up with, again, kind of fill in the blank sentences for each of these. Now, something I want to point out as important before we do this is I really, really want you to make sure that you're understanding what these fill in the blank sentences mean. I've noticed on some of our tests and quizzes, some of us are so focused on using the fill in the blank that then we make mistakes to the fill in the blank and then our sentence doesn't make sense anymore. So if you're going to try to use these, which they're a great tool, make sure that after you write your sentence, you read it. Does it make sense in context of the problem? Okay. And one way you might do that is just making sure that you understand why we use the fill in the blank sentences the way that we do. And if you're confused, let me know. I'd be happy to talk about it with you. So for the y-intercept, we're going to use this one. When x equals 0 in context. So for this, when there are 0 rubber bands, that's x equals 0 in context. The predicted, now y context, so the predicted distance traveled, sorry guys. So the predicted distance traveled is whatever your y-intercept is, so 25.3333 centimeters. That's it. So when there are 0 rubber bands, the predicted distance traveled is 25.3333 centimeters. All right, the next part of this is going to be the sentence for slope. So how are we going to interpret this slope? Starting out, I'll say with each additional x context. So what's important here is that we are saying with each additional one of the x's. So what we had said before was with each additional rubber band, you could say when you add one rubber band, when you increase the rubber band by one. It's just really important here that your x context, when you say additional, it's only by one. So with each additional rubber band, that's x context right there, the predicted y context, so the predicted distance traveled, increases or decreases, so this depends on if your slope's positive or negative, by whatever your slope is. So the one we did with each additional rubber band, the predicted distance traveled increases by 7.4638 centimeters. All right, so now pause the video, work on the check your understanding, then come back and I will again commentate through my earlier work of the check your understanding. But make sure you pause. Remember, this is your practice time. This is for you to make sure that you know what we're doing. All right, so we've got this problem. I'm going to assume you've read it because you're coming back from pausing. You're ready to go. Michael is a runner. He uses his Apple Watch to keep track of his distance and the number of calories he burns for 20 runs. A scatter plot of y equals calories burned and x equals distance in miles shows a fairly strong, positive, linear relationship. Wow, look at that. Strong, strength, positive, direction, linear, form. Awesome stuff. The regression equation models the data fairly well. And right there, I'm just plugging in what x and y mean in context of the problem. So y is calories, x is distance in miles. To interpret the slope, I'm going to use the equation from above. With each additional mile, I'm going to say with each additional mile, you could say mile run, the predicted, the predicted calories burned increases by 160 calories. So we've got our x context, our y context, increase, decrease, and the slope's value, 160 calories. All right, moving on. Does the value of the y-intercept have meaning in this context? If so, interpret the y-intercept. So I'm just going to get started and interpret the y-intercept at first, and then we can talk about does it have meaning. So for interpret, when Michael runs 0 miles, the predicted number of calories burned is 20 calories. And so what does it mean? Does it have meaning in this context? So think about the y-intercept in context of the problem. Does it make sense for 0 miles? Does it make sense for 0 miles to burn 20 calories? Can you run 0 miles? So here there's a little bit interpretation that you could use. If you don't think that makes sense, that's fine. You could probably get away with it as long as you explain yourself well. So making sure that you explain that the y-intercept does not have meaning in context of the problem because you can't run 0 miles or X, Y, and Z, whatever it is that you want to say. But you have to just explain yourself, right? Just like always, be very clear. So when you're considering if it has meaning in this context, really you're considering two things about the context. One being, does X equals 0 make sense? Eventually here, I'm going to make that note on this page. But essentially, the first thing you're going to look at, does X equals 0 make sense? Does it make sense to have 0 miles? Yeah, it could. I mean, I could just stand there and not run at all. And if I'm just standing, I might still burn calories. I mean, we naturally burn calories throughout the day. So the first thing I think is, does X equals 0 make sense? But then also, does the Y value make sense? So here, 20 calories, that makes sense. That's normal. But what if my y-intercept was negative 20 calories? Well, negative calories does not make sense. So here again, that's another example where the y-intercept would not have meaning because you can't have a negative y in context of the problem. So two things you check for. Can X equal 0? Does that make sense? And then the number that you get for the y-intercept, does that make sense? All right, so now we're going to predict if he were to run 5 miles. So I'm going to write it out. The predicted calories equals 20 plus 160 times 5. And I got 820 calories. That is his predicted value. Part D, now we know he actually burned 910. We are essentially finding his residual and interpreting it. So for RAP, R equals actual minus predicted, and the actual was 910. The predicted from above was that 820 equals 90. So 90 calories was his residual. And now we're going to interpret. So the actual calories burned was 90 calories above the predicted value for 5 miles. So the actual calories burned was 90 calories above the predicted value for 5 miles. I'm going to make that a little bit more clear because it looks like smiles. So I'm going to update it to look like 5. So for 5 miles. Again, that 5 miles is that X equals number portion of the interpret. All right, part E. Michael is thinking about signing up for his first marathon. So far, his longest run has only been 10 miles. Should he use the regression equation to predict how many calories he would burn if he runs a marathon of 26.2 miles? Explain. The answer here is no. He should not. No way. 26.2 miles is far outside the data he has collected. So we don't really want to use this to predict for 26.2 if the longest run he's ever done so far is 10 miles, right? And this is a really great example where we can think about why that might be the case, right? 10 miles might be totally doable, but more than 10, you might start to slow down. So it might not follow that line. This is an example of extrapolation, which is something that we do not want.